All right, let's go ahead and get started. I do want to welcome you to this worksheet. This is nuclear chemistry worksheet number 1. No need for a calculator or a periodic table or anything else for that matter. All you need is a pen, and we'll get started. Here we go. Penetrating power. What do we mean by penetrating power? We want to use the following diagram below to rank the penetrating power of the various radioactive sources in the boxes shown below. We want to look at beta particles, alpha particles, and gamma rays. So those three radioactive entities are going to be ranked now in terms of their ability to penetrate through various substances. So let's start with alpha particles. Now, alpha particles are fairly large. We can draw alpha particles as a helium nucleus, so I'll make it just like this. I'll put a 2 here and a 4 here, or I could have drawn it like that. So that's an alpha particle. Again, there is an inverse relationship between the size of the particle and its penetrating ability. So helium nuclei are pretty large, right? 2 protons and 2 neutrons, and they're fairly large. So they're not going to be able to penetrate very far. In fact, a single sheet of paper will stop an alpha particle, as you can see from the diagram. But how about beta particles? So beta particles are really electrons, right? A beta particle is an electron. We can write it as a beta like that, or we can write it like this, a 0 on top and a -1 down here. And they have much more penetrating power. They can easily go through paper, but they are stopped by an aluminum sheet. And finally, we have gamma rays. Now, gamma rays are not particles per se. They have no mass, but they do have energy. And they are capable of going through paper easily, even through aluminum very easily, but they're stopped by lead. So if we want to rank the penetrating power of these three things, we're going to say that the lowest penetrating power is going to be alpha particles. So alpha particles cannot go past, again, they will be stopped by, even a few centimeters of air will stop an alpha particle. And then the next thing is going to be beta particles or electrons. And finally, the one that has the most penetrating power are gamma rays, okay? So alpha particles, beta particles, and gamma rays from least to greatest penetrating power in that order. All right, let's move on. So we want to now look at the process called nuclear fission and compare it to fusion. It says nuclear fusion requires very hot temperatures and occurs naturally on the sun. So that's the place that we're almost certainly going to see nuclear fusion. So we'll say on the sun, just like that. Of course, we'll see it on other stars. And nuclear fusion has occurred on the Earth. There have been situations, for example, when we explode a nuclear bomb, fusion occurs in that process, but we see it naturally occurring on the sun. Nuclear fission, on the other hand, occurs in reactors. So reactor power plants or nuclear power plants are going to produce this process called fission, or the splitting of atoms, and is used to power nuclear submarines mainly. Okay, so we'll say nuclear subs, just like that. And it'll also be things like aircraft carriers, things like that, large transport vessels. Those are powered by nuclear fission. So the sun is nuclear fusion, again, require very, very high temperatures, and fission is going to be occurring in reactors and nuclear subs and things like that. So let's move on. Let's take a look at the process of nuclear fission and fusion, what they look like diagrammatically. It says nuclear fission and nuclear fusion, both are nuclear phenomena that release large amounts of energy, but they are different processes which yield different products. So from both of these, we're going to get a very, very large amount of energy. Identify fusion and fission in the diagram below. So let's start with the first diagram. So what do we have? We have deuterium and tritium. Deuterium and tritium slamming into each other at a very, very high rate of speed and producing helium. So when you have two things coming together, in this case deuterium and tritium, to form helium, a very, very large amount of energy, and a neutron, so the process can be propagated. When you have two things coming together, we're going to call that fusion. So the first one will be fusion. Now the second one on the right is uranium-235. In this case, what's going to happen is that the uranium-235 is going to be slammed by the little blue disk, or this little sphere is a neutron. So when you have that neutron hit the uranium-235 very, very fast, what's going to happen is that the uranium-235 is going to split into two smaller particles, in this case krypton and barium. And in doing so, you're going to form, again, huge amounts of energy, but also 3 more neutrons that are going to propagate this process. So again, when you split an atom like that, we're going to call that nuclear fission. So the second would be fission. One more time. Fusion, when two things come together to form one thing, in this case, the helium atom. And fission, when something breaks apart. So uranium-235 breaks into krypton and barium and breaks apart like that, we're going to call that fission. All right, let's take a look at some examples of fission and fusion. So there, we're being asked to choose here. The following are examples of nuclear either fusion or fission. So notice in all 3 cases, we're adding things up, right? In this case, it's these 2 isotopes of hydrogen to form helium. Helium and helium to form these 2. In this case, it's hydrogen and hydrogen to form hydrogen and a particle called a positron. But in all 3 of these cases, we're taking 2 things and putting them together to form something larger. And we're going to call that nuclear fusion, right? So nuclear fusion, when you put 2 things together to form one thing, and there's usually other products. Energy certainly is going to be a product, but we're also going to have beta particles, positrons, all types of other radioactive debris. The following is an example of a nuclear either fusion or fission. This time we're taking uranium-235 and we're hitting it with a neutron hard, and it's becoming strontium and xenon. And then 3 neutrons to propagate the process. Again, when you hit that uranium atom and split it into the strontium and xenon, that's going to be fission. So fusion is putting together, fission taking them apart. All right, let's finish up now. And so the question now is, we want to define finally nuclear fission and nuclear fusion. So the question is it fusion or fission when we break atomic nuclei into smaller pieces? That again is nuclear fission. Okay, so fission when we break it apart. The starting elements have a higher atomic number than that of the fission products. For example, uranium can fission to yield strontium and krypton. The second one says either fusion or fission joins atomic nuclei together. When you're joining them together, we're going to call that fusion. So the second one would be fusion. The element formed has more neutrons or more protons than that of the starting material. For example, hydrogen and hydrogen can fuse to form helium. So once again, fission when you're breaking things apart, fusion when you're putting them together. That'll do it for this one. I'll see you in the next one. Thanks. Bye-bye.